Welcome to the first episode of Einstein's Entanglement, a short video series based on the book Einstein's Entanglement, Bell Inequalities, Relativity, and the Qubit, published in 2024 by Oxford University Press. I'm your host and co-author of the book, Professor Stuckey. If you're interested in my credentials and why I began researching quantum foundations in 1994, you can check out my website listed in the video description. If you were interested in that intro music, it came from Professor Bob Kirk's demo for his quantum guitar. I have a link to that in the video description. He also developed a pictorial way of teaching quantum mechanics that has allowed high school students to successfully solve problems on an Oxford University postgrad exam after translating into their pictorial language. 50% of those 15 to 18-year-old students got distinction on the exam, which is a higher rate than the postgrad students. This is a picture of his book, Quantum in Pictures. This pictorial way of understanding the rules of quantum mechanics is even being used by quantum programmers and engineers to develop new quantum technology. Using the rules that govern the quantum pictures, Professor Kirk can show how quantum mechanics entails something called entanglement, what Amir Excel has called the greatest mystery in physics. So we know the rules of quantum mechanics lead to the greatest mystery in physics, as introduced by Einstein, Podolsky, and Rosen in 1935, but there is still tremendous controversy about how or why nature operates according to those rules to begin with. In this 5-part video series, I'm going to give you a very simple introduction to the mystery of Einstein's entanglement, and then I'm going to show you why nature operates according to those rules. In this first video, I'll give you an overview, and by the end of it, you will understand the revolutionary new way that quantum information theory can be used to solve the greatest mystery in physics. Professor Kirk's pictorial method for how to use the rules of quantum mechanics and the information theoretic explanation of why nature behaves in accord with those rules are products of the so-called second quantum revolution that began in the 1990s. Since you're watching this video, you're probably already familiar with the paradox of quantum entanglement as introduced by Einstein, Podolsky, and Rosen in 1935, as well as John Bell's famous inequality for the EPR paradox. Maybe you're even familiar with some of the bizarre solutions to this mystery, such as faster-than-light causal mechanisms like the pilot wave of Bohmian mechanics, or causal influences from the future creating effects in the present called retrocausality, or conspiratorial causal control of experimental procedures called superdeterminism, or the abandonment of agreement between observers, as in cubism, or that a single experimental measurement can produce all possible outcomes, as in the many worlds interpretation. The technical way to describe those proposed solutions to the mystery of Einstein's entanglement is if they violate locality, statistical independence, intersubjective agreement, or the uniqueness of experimental outcomes. You don't have to worry about the technical language in this video series. Just understand that it's widely believed that any solution to the mystery of Einstein's entanglement is necessarily going to entail what Einstein called spooky actions at a distance, or causes from the future, or superdeterministic control over experimental procedures, or infinitely many realities, or some crazy story that has existed for decades without garnering consensus support. Indeed, the effort to understand why nature behaves in accord with quantum mechanics began with the creation of quantum mechanics itself in 1925, and there is still no consensus explanation in sight. The reason for this endless debate is that most physicists and philosophers in quantum foundations want to understand the rules of quantum mechanics and solve the mystery of quantum entanglement via causal mechanisms, what Einstein called constructive efforts. I'll explain all of that in the next episode, episode 2. But there is another way to solve the mystery of Einstein's entanglement that Einstein himself used to solve the greatest mystery in physics at the end of the 19th century. That is, Einstein and his colleagues at that time tried to explain why everyone measures the same value for the speed of light, regardless of their relative motions, using constructive efforts, like the luminiferous ether, to no avail. Einstein eventually gave up in despair and turned to principal explanation, writing, "By and by I despaired of the possibility of discovering the true laws by means of constructive efforts based on known facts. The longer and the more despairingly I tried, the more I came to the conviction that only the discovery of a universal formal principle could lead us to assured results." His principal solution was trivial, really. He said the reason everyone keeps measuring the same value for the speed of light regardless of how they move relative to the source, is because of the relativity principle. That is, the relativity principle says the laws of physics must be the same in all inertial reference frames. And since c is a constant of nature according to Maxwell's equations of electromagnetism, everyone has to measure the same value for c, even if their perspectives on reality, their inertial reference frames, are moving relative to each other. Thus, his theory of special relativity was born in 1905. Notice importantly that Einstein did not say how nature makes that happen, only that it must be true if Maxwell's equations and the relativity principle are both true. That's the difference between a constructive explanation based on causal mechanisms and a principal explanation based on a compelling fundamental principle. And today, Einstein's principal solution to that mystery, the relativity principle, is so widely accepted that it appears in introductory physics textbooks like this excerpt from Surway and Jewett, even though we still don't have any consensus causal mechanism like the luminiferous ether to go along with it. I'll explain that in episode 3. At the dawn of the second quantum revolution in 1996, Carlo Rovelli challenged the quantum foundations community to match Einstein's feat. Rovelli wrote, "Quantum mechanics will cease to look puzzling only when we will be able to derive the formalism of the theory from a set of simple physical assertions, postulates, principles about the world. Therefore, we should not try to append a reasonable interpretation to the quantum mechanics formalism, but rather to derive the formalism from a set of experimentally motivated postulates." You can see from the second half of this quote that he was inspired by Einstein's physical understanding of the Lorentz transformations, which then became the formalism of special relativity. Since Einstein created that physical understanding in principal fashion, Rovelli is suggesting that we view quantum mechanics as a principal theory as well. Specifically, quantum mechanics should be viewed as a principal theory that follows from an experimentally motivated postulate, like the light postulate, rather than a constructive theory about causal mechanisms dictating the behavior of quantum objects. As Philip Goyal pointed out, Rovelli was suggesting that we reconstruct the Hilbert space formalism of quantum mechanics exactly like Einstein reconstructed the Lorentz transformations leading to special relativity with its profound reconceptualization of the nature of space and time. It's generally agreed that Lucien Hardy was the first to successfully answer Rovelli's challenge in 2001 with his paper, Quantum Theory from 5 Reasonable Axioms. And today, there are many so-called axiomatic reconstructions of quantum mechanics based on information theoretic principles. Here's a sample from one of our recent papers. But despite the success of these information theoretic reconstructions of quantum mechanics, we still don't have a consensus solution to the mystery of Einstein's entanglement. That's because the experimentally motivated postulate at the basis of the quantum reconstructions is the equally mysterious quantum bit of information, or qubit. What makes the qubit mysterious is how it differs from the classical bit, like that in everyday computers. And that difference is a property called quantum superposition. You might have been introduced to quantum superposition by Schrödinger's cat that is simultaneously both dead and alive. Now, the quantum foundations community already knows very well that the mystery of quantum entanglement follows from the mystery of quantum superposition, as Professor Kirk can show with his quantum pictures. So basing the reconstruction of quantum mechanics on qubit superposition didn't do anything to solve the mystery of Einstein's entanglement. But that doesn't mean the quantum reconstruction program is worthless. Far from it. That's because these information theoretic reconstructions showed us that the Hilbert space formalism of quantum mechanics with its entangled states could be derived from the qubit. And that means if you can somehow solve the mystery of qubit superposition, you will have a physical understanding of the entangled states of quantum mechanics, thus solving the greatest mystery in physics. I will explain all that in episode 4, but spoiler alert, the mystery of qubit superposition is also the result of the relativity principle. As it turns out, the way that quantum information theorists characterize the qubit via information invariance and continuity makes it obvious that the mystery of qubit superposition reduces to the mystery of the observer independence of yet another constant of nature, Planck's constant h from Planck's radiation law. So in perhaps the greatest irony of physics, the mystery of Einstein's entanglement can be solved in principal fashion, exactly like Einstein solved the mystery of the observer independence of the speed of light c, with Einstein's own relativity principle. Pedagogically, The quantum reconstruction program leads to a new way of introducing quantum mechanics and introductory physics. Here, for example, is how Randy Knight could mirror his introduction to special relativity for an introduction to quantum mechanics. So the second quantum revolution has produced entirely new ways to understand why nature behaves per the rules of quantum mechanics and how we can use those rules to produce new technologies like quantum computers and quantum cryptography. Now that we understand the twin pillars of modern physics, special relativity and quantum mechanics, are both principal theories with no consensus causal counterparts, where does that leave constructive explanation? What does it mean to say that reality is ultimately based on a fundamental principle rather than a fundamental force or causal mechanism? I will speculate on the answers to those questions in the last episode of the series, episode 5. But the short answer is found in the matrix. Neo-decipher. What does that mean? Cipher. It means buckle your seatbelt, Dorothy, because Kansas is going bye-bye. So take the red pill, stay in Wonderland with me, and buckle your seatbelt, because you're about to leave Kansas and enter Einstein's entanglement.